Hello everyone. In this video, we will talk about a new topic, optimization. On the textbook, this part of material is in Chapter 7. First, we talk about a method called golden section search. Golden section search is also called golden mean search. This method belongs to the bracketing method. The golden mean search is simple, robust, and straightforward. It first takes an interval a to b such that it's known that there is a single minimum on this interval, and then we select 2 points on the interval c1 and c2 and compare the function value at c1 and c2 to determine whether the root lies on the interval a to c1 or on the interval c1 to b. Then we repeat this process until the interval becomes sufficiently small. When we use this method, it involves a concept called the Codon Ratio. So let's first review what's Codon Ratio. Euclid's definition of the Codon Ratio is based on dividing a line into 2 segments so that the ratio of the whole line to the larger segment is equal to the ratio of the larger segment to the smaller segment. This ratio is called the Codon Ratio. For example, as shown in this figure, we have the larger segment L1 and the smaller segment L2. So the ratio of the whole line, which is L1 plus L2, to the larger segment L1 is equal to the ratio of the larger segment L1 to the smaller segment L2. And then, based on this equation, we can calculate the ratio between L1 to L2. So first, we multiply both sides by L1 times L2. So the left-hand side becomes L2 times L1 plus L2. And the right-hand side becomes L1 squared. Then we can move everything to the left-hand side. We have L2 L1 plus L2 squared minus L1 squared equal to 0. Then we can divide both sides by L2 squared. So we have L1 over L2 squared minus L1 over L2 and minus 1 equal to 0. Then we can use the formula to find the root of this second order equation. So L1 over L2 will be equal to negative 1 plus or minus the square root of 1 plus 4. Just use the root for the formula to find the root. So we have L1 over L2, which should be positive. So this should be 1 plus the square root of 5 over 2, and which is 1.618034, etc. So this value is called phi. It's the golden ratio. We will use this value when we use golden section search method to find the local minimum or maximum. Okay, and then the problem we want to solve, given a function of one variable fx, we want to find the local minimum of that function. The assumptions, we assume that the function fx is continuous. Initial requirements, we start with an initial bound a to b, which contains a single minimum. Then the iteration process, given the interval a to b, we define 2 interior points, C1 and C2. C1 is defined as phi minus 1 times A plus 2 minus phi times B. And C2 is defined as 2 minus phi times A plus phi minus 1 times B. And then there are 3 different scenarios. So the first, assume that we have a function like this. So this is the initial bound a to b. Then we find 2 interior points C1 and C2, right? When we compare the function value at C1 and C2, if FC1 is exactly equal to FC2, and then we cannot continue this iteration process because we are not sure where the minimum is located. So we need to halt because we can't continue searching. So if that happens, we need to change the initial bound A to B, right? Find a different initial interval. The second scenario is that if C1 is less than C2, for example, as shown here, if we have a function so this is A, this is B, and this is C1, this is C2. So FC1 is less than, so this is first scenario, this is the second scenario. So when FC1 is less than FC2, then the minimum must lie on the interval from A to C2. Then we can assign this B to this, replace this C2, because in each iteration we always start from A to B, right? So the third scenario is that when FC1 is larger than FC2. So for example, we have this function. So here is A, here is B, then we have C1, this is C2. So you can see C1 is larger than C2, then we know that the minimum must be from C1 to B, right? Then we can assign the make this the value of C1 as the new variable A, right? So A will be updated. This is the third scenario. And then when we have this new A to B, we can always start the next iteration and repeat the whole process, all right? Okay, so why we need to choose the interior points C1 and C2 like this? So let me show you why we use the formula here. You can see this C1 is equal to this specific value and C2 is equal to this specific value. So why they have to be like that? It's actually designed to save computation time, to speed up the process. It's not because it's more accurate or more reliable, it's because the speed. So let me show you. If you use C1 and C2 as defined in the formula, it actually looks like this. So we have a interval A to B. So this is the C1, this is the C2. So if you use the C1 as defined in the formula, this part will be 0.382 of the whole length from A to B. Assume that A to B, the whole length is 1. And then this length will be 0.382. And this length will be 0.618. All right. So the good thing about this specific 2 points is that when you repeat the process in the second iteration, for example, we found that the minimum is in the interval from A to C2, right? Then this C2 becomes the new B, and then we need to do the iteration again. So when you find the interior point C1 and C2, this C2 is exactly the same with the old C1, because the function value at the C1 is evaluated in the last iteration. So when it becomes C2, in this iteration, we don't need to evaluate the function value at this point again because it's already evaluated in the last iteration. So we can save the computation time, right? All right. So for example, if you decide in this interval, we decide that this will be the A to B, right? Then we find C1 and C2. So this C2 will be exactly equal to the C1 in the last iteration. So we don't need to evaluate the function value at this point again. Okay, so that's the point of using these specific value for C1 and C2 because we want to speed up the process, especially when people don't have computers. They use hand calculation. By selecting these 2 points can save them a significant amount of time. Okay, so let's see an example about if we use other interior points, then what happens. Okay, so for example, if we use A, B, we use C1 and C2. For example, assume A to B is exactly 1, then A to C is 1/3, and A to C2 is 2/3, right? So if you use this and follow the iteration process, you can still find the location of the minimum, but it will take a longer time. Let's see what happens. So from A, C1, C2, B, for example, initially assume the whole length is 1, and C1 is 1/3, C2 is 2/3, right? And in the next interval, assume that the minimum located from the interval from A to C2, then A will be 0, the new B will be 2/3, right? Then we need to find this point, and this point will be 2/9 because this point will be will be the total length 2/3 times 1/3, right? And this point C2 will be 2/3 times 2/3, so it's 4/9, right? And the 2/9 and 4/9, the function value at these 2 points were never evaluated before, so we have to evaluate the function value at these 2 points, right? Assume that we found the minimum is located from 0 to C2, which is 4/9. So 4/9 will be the new B, right? And then in this interval, here should be 4/9 times 1/3, right? Which is 4/27. And and the C2 will become 4/9 times 2/3, which will be 8/27. So 4/27 and 8/27 are also new values, right? So we need to evaluate the function value at these 2 points. And in contrast, if you use the Codon ratio, for example, from A to B, we have C1, C2, right? So you assume that the length from A to B is 1, and then C1 will be 0.382, C2 will be 0.618, and then assume that we found the minimum is located from A to C2, so the new B becomes the value of C2, 0.618. So the value of C1 in this iteration will be the total length 0.618 times 0.382. So this will be 0.236. And the C2 will be the total length 0.618 times 0.618. So let's calculate this. 0.618 squared. So this will be 0.382, right? So this will be 0.382. So you can see 0.382, the function value at this point is already evaluated, right? Because when we do the first iteration, we evaluated FC1 and FC2. So when we do the second iteration, we still need to evaluate this point, but here the FC2 is exactly equal to the FC1 in the last iteration. So we don't have to evaluate again, so it saves a lot of time, right? For example, we found that the minimum located from A to C2, then in the next iteration, we are from 0 to 0.382, right? And then this point, C1, will become the total length, 0.382 times 0.382. So let's see, 0.382 squared, this will be 0.146. And the C2 will become the total length 0.382 times 0.618. So 0.382 times 0.618, it will be 0.236. So you can see that this 0.236, this FC2 has already been evaluated in the last iteration, right? So we don't need to evaluate this value again, right? If you repeat this process from 0, for example, C2, right, 0.236. So here, this value C1 should be 0.236 times 0.382, right? 0.236 times 0.382. This will be 0.090. And this point will be 0.236 times 0.618. So let's see. So this value will be 0.146. So you can see when we evaluate the function value at this point, we don't need to calculate it because the function value at this point is already evaluated in the last iteration, right? So it can save us a lot of time. So that's the whole point of using Codon Ratio as interior as a method to find the interior points. In the next video, we will talk about the halting condition of this method.